On the nights of November 16th and 17th, 2025, telescopes in New Mexico captured something that shouldn't exist. The images show jet streams of material blasting outward from an object called 3I Atlas, shooting in every conceivable direction. Some point away from the sun, which makes sense. Others point sideways, which is unusual. And then there are jets pointing directly toward the sun, which challenges traditional comet models. This isn't a blurry photograph from an amateur with a backyard telescope. This is professional grade data, captured by calibrated instruments, processed by experienced astrophotographers, and it's forcing scientists to confront a possibility that makes everyone uncomfortable. We might be looking at something that doesn't fit our models of natural objects. Stay with me, because what I'm about to show you isn't speculation or clickbait. It's documented evidence that's generating significant interest and debate within parts of the astronomical community. Let me be absolutely clear about what we're dealing with. These images from New Mexico aren't the first observations of 3I Atlas. This object has been tracked for months, moving through our solar system on a trajectory that came from somewhere beyond our sun's influence. It's one of only 3 confirmed interstellar visitors we've ever documented, and from the moment it was spotted, it behaved strangely. But these new images, these particular photographs taken in mid-November, they've elevated the strangeness to something approaching impossible. The jets you're seeing aren't subtle. They're not artifacts of image processing or tricks of perspective. They're real structures extending outward from a central nucleus, and their directions defy the basic physics that governs every comet we've ever studied. Now, before you think this is going to be another Aliens Built It video, let me set expectations. I'm not here to tell you what 3I Atlas is. I'm here to walk you through what we're seeing, why it challenges conventional explanations, and what scientists both mainstream and unconventional are saying about it. The truth is, nobody knows for certain what this object is. What we do know is that it's behaving in ways that natural comets shouldn't, and that fact alone demands our attention. Science advances not when we find answers that confirm what we already believe, but when we encounter evidence that forces us to question our assumptions. And right now, 3I Atlas is doing exactly that. The telescopes that captured these images were operated by astrophotographer Satoru Murata and Francois Kugel, working with Celestron Edge HD equipment, specifically 0.2 meter and 0.4 meter telescopes. These aren't toys. They're precision instruments capable of capturing fine detail across long exposures. The exposures themselves range from 60 seconds to several minutes, allowing the cameras to gather enough light to reveal structures that would be invisible to the naked eye. Multiple exposures were stacked, a standard technique in astrophotography that reduces noise and enhances genuine features while cancelling out random artifacts. What emerged from this process were images showing a complex multidirectional jet structure that has no easy explanation. When you look at these photographs, and I mean really look at them, you see something that immediately triggers cognitive dissonance. There's the main tail, tightly collimated, extending in one direction as you'd expect. But then there are these other jets, fanning outward at odd angles, and most troubling of all, there's what astronomers call an antitail, a jet of material pointing back toward the sun, the very source of radiation pressure that should be pushing everything away. Antitails aren't completely unknown in comet science. Sometimes the geometry of Earth's viewing angle relative to a comet's orbit creates an optical illusion that makes dust trails appear to point sunward. But those illusions only work from specific viewing angles at specific times. 3I Atlas has been showing this sunward jet behavior across multiple observation periods spanning months. It's not a geometric trick, it's physically there. And it shouldn't be. Here's what makes this so important. We live in an era where space is no longer an abstract frontier. We've sent probes beyond our solar system. We've landed robots on comets. We've mapped the surfaces of distant moons in detail that would have seemed like science fiction just decades ago. We understand comet physics, or at least we thought we did. The fact that an object can enter our solar system and violate those physics in such obvious, documented ways means one of two things. Either our understanding of comets is far more limited than we believed. 3I Atlas isn't following the same rules because it isn't the same type of object. Both possibilities are profound. One means we've been fundamentally wrong about a category of celestial bodies we've studied for centuries. The other means we're looking at something unprecedented, something that might not have formed through natural processes at all. I want you to think about where you are right now as you're hearing this. Maybe you're at home, scrolling through videos looking for something interesting. Maybe you're commuting, passing time. Whatever your situation, you're part of a global network of people watching this unfold in real time. Somewhere right now, a telescope is pointed at 3i Atlas, gathering more data. Somewhere, a scientist is analysing spectroscopic readings, trying to make sense of chemical signatures that don't match typical comets. Somewhere, a team is running simulations, trying to model how natural processes could produce what we're seeing. And all of us, professional astronomers and curious observers alike, we're all witnesses to something we can't fully explain. That's a rare position to be in. Science usually moves slowly, processing old data, refining old theories. But occasionally something happens that's genuinely new, genuinely mysterious. 3i Atlas is one of those moments, and those images from New Mexico, they're not the end of the story. They're the beginning of a much deeper question. Let me describe exactly what these images show, because the details matter. In the center of each frame, there's a bright nucleus, the solid core of the object, or at least what appears to be solid. From that nucleus, multiple distinct features extend outward. The most prominent is the main tail, which shows a level of collimation that catches the eye immediately. Collimation means the stream of particles is tightly focused, almost like a beam rather than a diffuse cloud. Comet tails can be relatively narrow, especially gas tails aligned with magnetic field lines. But the degree of focus seen in 3i Atlas's main tail is at the extreme end of what we'd expect. It doesn't spread out and dissipate the way most comet tails do as they extend farther from the nucleus. Instead, it maintains its coherence across a remarkable distance. Then there are the secondary jets. These appear as fainter structures branching off at angles that don't correspond to any simple model. If you're imagining a comet as a dirty snowball that heats up on one side, the side facing the sun, then you'd expect jets to originate from that heated hemisphere and point generally away from the sun. The rotation of the nucleus might cause those jets to sweep across space like water from a rotating sprinkler, but averaged over time, the overall direction should still be away from solar radiation. What the New Mexico images show is different. Jets extend outward in multiple directions simultaneously, as if the entire surface is outgassing at once, or as if multiple discrete regions are active independent of solar heating patterns. The antitail is particularly striking. It appears as a narrow structure extending in the direction opposite to the main tail back toward the sun. Now, I mentioned earlier that antitails can be optical illusions, but let me explain why that explanation fails here. When a comet moves through its orbit, it leaves behind a trail of dust particles. These particles don't immediately fly away. They linger in the comet's orbital path, gradually spreading out due to slight differences in their velocities and solar pressure effects. If Earth happens to pass through the plane of that dust trail, or if our viewing angle aligns just right, we can see that trail edging, and it might appear to point toward the sun even though it's actually just an old trail lying in the orbital plane. This is a well-understood phenomenon. It's happened with several comets, and once you account for orbital geometry, the mystery dissolves. But here's the problem with applying that explanation to 3i Atlas. The antitail has been observed across multiple months, and from observations at different points in Earth's orbit. In July and August of 2025, when 3i Atlas was first generating significant interest, observers noted unusual tail structures. Now, in November, months later, with Earth having moved significantly in its orbit, and 3i Atlas having moved even more dramatically along its hyperbolic trajectory, the sunward jet persists. It's not a viewing angle artifact. The object is genuinely ejecting material in a direction it shouldn't. Solar radiation pressure, the force of photons from the sun, impacting dust particles should push material away. The solar wind, a stream of charged particles flowing outward from the sun, should also push gas and ionized particles away. For material to move sunward, it would need to overcome both of these forces. The only natural mechanism we know that can do this is gravity itself, if the dust particles were massive enough. But dust particles in comet tails aren't massive enough. They're tiny, lightweight, and easily pushed by radiation pressure. So what force is driving material toward the sun? Satoru Murata, one of the astrophotographers who captured these images, has decades of experience imaging comets and asteroids. He knows what normal looks like. He knows the difference between real features and processing artifacts. When someone with that level of expertise releases images showing multidirectional jets and says, essentially, this doesn't fit, it carries weight. Francois Kugel, his colleague in these observations, brings additional credibility. Both have worked with observatories and contributed to databases of asteroid and comet observations used by professional astronomers worldwide. These aren't fringe figures making extraordinary claims without evidence. They're careful observers presenting data and acknowledging that the data is strange. The exposure times used in capturing these images are worth noting because they speak to the object's brightness and activity level. Exposures ranging from 1 to several minutes mean that 3i Atlas is producing enough reflected sunlight and possibly enough intrinsic emission from fluorescing gases to register clearly on camera sensors. That level of activity requires energy. In a typical comet, that energy comes from the sun heating the surface, causing ice to sublimate into gas, which then escapes into space, carrying dust particles with it. The brightness we see is a combination of reflected sunlight off those dust particles and fluorescence from excited gas molecules. The fact that 3i Atlas is bright enough to photograph with these exposure times tells us it's actively outgassing, actively producing a coma, the fuzzy cloud surrounding the nucleus, and actively generating these jet structures. What's also significant is the consistency of observations. Over the 2 nights in mid-November, the jet structures appeared in multiple frames. This isn't a one-off image that might be explained by a random fluctuation or a brief event. The features are persistent, across hours, suggesting they represent stable or semi-stable outgassing patterns. In comet science, stable jets often indicate active regions on the surface where ice is exposed and sublimating. But stable jets pointing in directions that defy solar heating patterns suggest something else is controlling where and how the outgassing occurs. Internal heat sources, structural features that channel gas flow in specific directions, composition variations that cause different regions to respond to sunlight differently. All of these are possibilities, but none of them fit easily into standard comet models. The images also reveal structure within the jets themselves, variations in brightness, possible embedded knots or clumps of material, and the aforementioned collimation. When gas and dust are expelled from a comet nucleus, the flow typically becomes less organized as it moves farther out. Random collisions, radiation pressure, and the expanding gas all contribute to spreading and diffusion. The fact that these jets maintain definition suggests the initial outgassing velocity is high and the flow is directional from the start. High-velocity jets are known in comets. Sometimes sublimating gas accelerates quickly through narrow vents or fractures. But again, we're talking about scale and consistency here. The jets in these images aren't subtle wisps. They're prominent features extending across significant portions of the frame, and they're doing so in multiple directions at once. And this brings us to a crucial point. What we're seeing in these images is the result of processes happening on and within 3i Atlas right now. This isn't ancient history captured in rock layers or faint signals from distant galaxies. This is an object that's here, in our solar system, close enough to photograph in detail, and it's actively doing something we can't fully explain. That proximity and that activity level give us an opportunity that's vanishingly rare in astronomy. We can study this object in real time. We can track how its behavior changes as it moves closer to or farther from the sun. We can analyze the light reflecting off its surface and the light emitted by its gases. We can refine our measurements of its trajectory and mass. Every piece of data we gather adds to the puzzle, and right now the puzzle pieces aren't fitting together the way they should. That's not a failure of observation, it's an invitation to investigate deeper. To understand why 3i Atlas is so puzzling, you need to understand what comets normally do. And the good news is, comet behavior is actually pretty straightforward when you break it down to basics. A comet is essentially a chunk of ice mixed with rock and dust, often described as a dirty snowball, though that's an oversimplification. These objects form in the cold outer regions of solar systems, where temperatures are low enough for water, carbon dioxide, methane, and other volatile compounds to freeze solid. For most of a comet's existence, it's just a frozen lump drifting through space, inert and dark. But when a comet's orbit brings it close to a star, everything changes. As a comet approaches the sun, solar radiation begins to warm its surface. Ice doesn't melt in the vacuum of space it sublimates, meaning it transitions directly from solid to gas without passing through a liquid phase. This process starts slowly when the comet is still far out, maybe beyond Jupiter's orbit, and accelerates dramatically as the comet gets closer. The gas escaping from the surface carries dust particles with it, creating the fuzzy coma that makes comets visible and distinct from asteroids. As more gas and dust are released, they form tails, actually two distinct types of tails, each with different physics. The dust tail is made of solid particles ranging from fine powder to small pebbles. These particles are pushed away from the sun by radiation pressure, the physical momentum carried by sunlight photons. Because dust particles have mass and inertia, they don't accelerate instantly. They're pushed gradually, and their paths curve gently as the comet moves along its orbit. This creates the classic broad, sweeping dust tail that curves slightly behind the comet's motion. The dust tail always points generally away from the sun, but because of these momentum effects, it doesn't point exactly radially outward. There's a lag, a curvature that tells astronomers about the particle sizes and the comet's motion. The gas tail is different. Also called the ion tail or plasma tail, it's composed of ionized molecules, atoms, or molecules that have lost electrons due to ultraviolet radiation from the sun. These charged particles interact with the sun's magnetic field, which is carried outward by the solar wind, a stream of charged particles flowing from the sun at high velocity. The ion tail is shaped and directed by this magnetic field structure. Because magnetic forces are much stronger than radiation pressure for these lightweight charged particles, the ion tail is typically straight and points almost exactly away from the sun. It can extend for millions of kilometers, sometimes stretching across significant fractions of our field of view when a bright comet passes near Earth. Now, here's the critical part. Both types of tails point away from the sun. Not away from the comet's direction of motion away from the sun. If a comet is approaching the sun, its tails stream behind it. If a comet has rounded the sun and is heading back out, its tails still point away from the sun, meaning the comet is actually chasing its own tails as it recedes. This isn't intuitive until you remember that the tails aren't caused by the comet's motion through space. They're caused by solar radiation and solar wind-pushing material outward from the sun. The sun is the dominant force shaping comet tails, and that force always pushes outward. So when you see jets shooting toward the sun from 3i Atlas, your brain should immediately flag that as wrong. There's no known mechanism in standard comet physics that produces sustained sunward jets. You might get occasional transient events outbursts, where trapped gases suddenly vent due to internal pressure, shooting material in directions determined by the structure of the vent rather than solar forces. But those are brief, explosive events, not sustained jet structures visible across multiple observation nights. And even in outburst events, the material expelled sunward would quickly be overtaken by radiation pressure and solar wind, reversing its direction within hours or days. For a sunward jet to persist, something would have to be continuously driving material against the outward forces, and there's no natural comet mechanism that does that. Let's talk about the rotation issue, because it's relevant to the multidirectional jets. Comet nuclei rotate, typically with periods ranging from hours to days. As the nucleus rotates, different regions come into sunlight, heat up, and begin outgassing. If an active region, a spot where ice is particularly exposed, or where subsurface ice is close to the surface, rotates into sunlight, it starts venting gas. As the nucleus continues rotating, that region vents continuously, and because the nucleus is rotating, the jet sweeps across space. From a distance, this can create a spiral pattern in the coma or tail, like water from a rotating lawn sprinkler. Astronomers have observed this effect in many comets, and it's well understood. But here's what's strange about 3i Atlas. The jets appear to extend in multiple directions simultaneously without the kind of spiral structure you'd expect from rotation-modulated venting. It's as if multiple active regions are all firing at once, in different directions, regardless of whether they're in sunlight or shadow. Comets do have multiple active regions, patches of exposed ice scattered across the surface, but those regions should be primarily or exclusively on the sun-facing hemisphere. The night side of a comet nucleus, the side facing away from the sun, should be cold and largely inactive. Any jets originating from the night side would have to be driven by internal heat or by sublimation of super volatile materials that don't require direct sunlight, and while that's theoretically possible, it's not common and it doesn't explain the scale of activity we're seeing. There's also the matter of collimation. When gas vents from a comet, it expands into the surrounding vacuum. Expansion tends to diffuse the flow, spreading it out. For a jet to remain narrow and well-defined, The outgassing must be focused perhaps through a narrow vent or a subsurface cavity that channels the flow. This happens in some comets, particularly when fresh ice is suddenly exposed by fractures or when cavities collapse. But again, we're talking about scale and number. 3I Atlas appears to have multiple highly collimated jets, including the main tail and these secondary structures, all maintained across distances that should see significant diffusion. The level of organisation in the outgassing is higher than what we typically see, and that raises questions about the internal structure of the object. All of this comes back to a fundamental principle. In comet physics, the sun is the primary external energy source. Solar radiation heats the surface, drives sublimation, and along with solar wind and radiation pressure, shapes the resulting coma and tails. If you want to predict what a comet will do, you start with its distance from the sun, its rotation state, and its composition. Those factors give you a baseline expectation. Deviations from that baseline suggest either unusual composition, maybe exotic ices that sublimate at different temperatures, or unusual structure, maybe internal voids or layered composition, or, in extreme cases, something other than solar heating driving the activity. 3I Atlas deviates from the baseline in multiple ways simultaneously. Sunward jets, multidirectional outgassing, highly collimated tails, and other anomalies related to its mass, composition, and behaviour, all combine to paint a picture that doesn't fit the standard comet model. Individually, each anomaly might be explained with some creative thinking and special pleading, but collectively, they form a pattern that suggests we're either missing something fundamental about how comets can behave, or we're looking at something that isn't governed by the same physics because it isn't the same type of object. Either way, these images from New Mexico are visual proof that our assumptions are being challenged. And in science, that's when things get truly interesting, because it's only when our models fail that we're forced to build better ones. Let's go deeper into this jet direction issue, because it's not just a minor oddity, it's a fundamental challenge to our understanding. I've explained that comet tails should point away from the sun due to radiation pressure and solar wind. I've mentioned that rotation can cause jets to sweep across space. But there's a level of detail here that makes the 3I Atlas observations even more problematic, and it has to do with sustained directionality over time and distance. When a comet nucleus rotates and an active region vents gas, the jet that forms points in a direction determined by the vent's orientation on the surface. If that vent is on the sun-facing side and points roughly outward from the nucleus, the jet will align with the direction away from the sun, and radiation pressure will reinforce that direction. But if the vent is angled, or if it's on the limb of the nucleus where sunlight strikes at a grazing angle, the jet might initially point at an angle that doesn't align with the anti-solar direction. For a brief period, you could have a jet pointing sideways or even slightly sunward, driven by the pressure of expanding gas rather than by solar forces. Here's the catch: that only works for the immediate vicinity of the nucleus. Once the gas and dust travel more than a few kilometers from the surface, solar radiation pressure takes over. Dust particles, which are small and lightweight, begin to feel the push of sunlight. Within hours, they're redirected. Within days, they're fully integrated into the broader tail structure, which always points away from the sun. So even if you have a weirdly angled vent creating an initially misdirected jet, that jet should dissipate and blend into the normal tail within a short distance and a short time. The sunward jet observed in 3I Atlas doesn't do that. It extends visibly in the anti-solar direction across distances that should be well within the radiation pressure regime. It persists across observation periods separated by months. This isn't a transient feature visible for a few hours due to an unusual vent. This is a stable or semi-stable structure that's actively maintained against the forces that should be destroying it. For that to happen, there would need to be a continuous source of momentum driving material sunward, overpowering radiation pressure. In natural comets, there's no such source. Now let's address the geometric illusion explanation more thoroughly, because it's the most common counterargument, and it deserves serious consideration. As I mentioned earlier, anti-tails can appear in comets due to viewing geometry. Here's how it works in detail. As a comet orbits, it sheds dust particles. These particles don't fly away instantly. They drift slowly, spreading out along the comet's orbital path. This creates a sheet or stream of dust particles lying in the plane of the comet's orbit. Most of the time we view this dust sheet from an angle, and it just looks like part of the broad dust tail. but occasionally Earth's orbit crosses the plane of the comet's orbit, or nearly so. When that happens, we see the dust sheet edging, and it appears as a narrow spike of light extending in the direction opposite to the main tail. It's not actually material moving sunward, it's old material lying in the orbital plane that appears to point sunward from our perspective. This phenomenon is real and well documented. Comet Arend-Roland in 1957 displayed a prominent antitail caused exactly by this geometry. When astronomers calculated the viewing angles and orbital positions, the mystery evaporated. The antitail was just an artifact of perspective. So when 3i Atlas started showing an antitail, the natural first assumption was that the same explanation applies. Calculate the orbital geometry, check the viewing angles, and the problem should go away. Except it didn't. Observers tracked 3i Atlas over multiple months from its initial detection through perihelion and beyond. During this time, Earth moved along its orbit, changing our viewing angle relative to 3i Atlas's trajectory. 3i Atlas itself moved along a hyperbolic path, a path that's not a closed ellipse like typical comets, but an open curve that brings it into the solar system once and then sends it back out into interstellar space, never to return. The changing geometries should have caused any perspective-based antitail to appear and disappear, to change in intensity and orientation as the alignment shifted. Instead, the sunward jet persisted. It was observed in July when 3i Atlas was approaching perihelion. It was observed in August as it rounded the sun. And it was observed again in November, captured in these New Mexico images, after perihelion, with Earth and the object both in entirely different positions. This persistence across changing geometry strongly suggests the antitail is a real, physical jet of material moving sunward, not an optical illusion, and that's deeply problematic. To move material sunward requires a force. The expanding gas pressure from sublimation could, in theory, accelerate particles in any direction, including sunward, if the vent is oriented correctly. But once those particles leave the immediate vicinity of the nucleus, they're exposed to solar radiation pressure, which would decelerate them, stop them, and eventually push them back. For a visible jet to extend sunward across thousands or tens of thousands of kilometers, you'd need continuous mass ejection, with enough velocity to overcome radiation pressure, not just initially, but across the entire visible length of the jet. That requires sustained, directed thrust, and the energy budget for that level of activity is enormous. Now let's consider the multidirectional nature of the jets as a whole. It's not just the sunward jet that's strange, it's the fact that jets appear to radiate in multiple directions simultaneously. In a normal comet, you might see jets active on different parts of the nucleus as it rotates, but the integrated result, what you see when you take a long exposure photograph, is a more or less symmetric coma, and tails pointing in the expected directions. The rotation averages out the directional variations. For 3i Atlas to show discrete jets extending in multiple distinct directions in the same image suggests either very rapid rotation, with very active, discrete vents, or simultaneous outgassing from multiple regions regardless of solar heating patterns. Rapid rotation is theoretically possible, but it comes with limits. Rotate too fast and centrifugal forces start to overcome the object's self-gravity, potentially tearing it apart. For a small object like 3i Atlas, which is relatively modest in size, there's an upper limit on rotation speed before structural failure. If the rotation is fast enough to create the observed multidirectional jets through time averaging, we should see other evidence of that rotation periodic brightness variations, for example, as different surface areas reflect sunlight toward us. Some rotational variations have been observed, but nothing that obviously explains the jet structure. Simultaneous outgassing from multiple regions is also possible if the object has a very heterogeneous surface composition. Maybe there are patches of different types of ice, some water ice, some carbon dioxide ice, some even more volatile materials, and each responds to sunlight differently. As different patches reach their sublimation temperatures, they activate at different times and from different surface locations, creating multiple active regions. But even in this scenario, you'd expect the jets to preferentially originate from the sun-facing hemisphere and point generally outward. You wouldn't expect significant activity on the night side, and you certainly wouldn't expect jets pointing toward the sun. There's also the question of how these jets maintain their collimation over such distances. Imagine squeezing a water balloon and watching a jet of water shoot out through a small hole. The jet starts narrow, but it quickly spreads out and breaks into droplets due to surface tension and air resistance. In the vacuum of space, there's no air resistance, but there's still the tendency of expanding gas to spread out. For a jet to stay narrow, it needs to be confined either by surrounding gas pressure, by magnetic fields, or by initial velocity so high that the expansion time is longer than the travel time across the observed jet length. In comet environments, magnetic fields are weak and don't significantly confine jets. Surrounding gas pressure exists in the dense inner coma but drops off rapidly with distance. That leaves initial velocity as the primary factor maintaining collimation, and to get high initial velocity, you need high gas pressure at the vent, which means either very rapid sublimation or some kind of subsurface cavity, where gas accumulates before venting explosively. Both scenarios are possible for brief outbursts, but maintaining collimated jets steadily across observation periods spanning months suggests something more stable, something that's providing consistent directed outgassing. All of these details compound the mystery. It's not just one weird feature that needs explaining, it's a constellation of features, each individually unusual, that together form a pattern inconsistent with standard comet behavior. And the New Mexico images capture this pattern in stark visual terms. You don't need to be an astrophysicist to look at those photographs and feel that something is off. The human brain is excellent at pattern recognition, at sensing when something doesn't fit the expected template. These jets pointing in multiple directions, maintaining their structure, persisting over time, they trigger that sense of wrongness. And in this case, that instinctive reaction aligns with the detailed analysis. The math and physics confirm what your eyes suggest. This isn't behaving like a normal comet. Now we need to talk about energy, because everything we've discussed so far, the jets, the outgassing, the brightness of the coma, all of it requires energy. And in comet physics, there's one primary source of energy, the sun. Solar radiation heats the surface, ice sublimates, gas expands, dust is carried along. It's a chain of events driven by incoming sunlight, and that chain has quantifiable limits. You can calculate how much energy a comet nucleus receives based on its distance from the sun and its size. You can estimate how much of that energy goes into sublimating ice, and from that, you can estimate how much gas and dust should be expelled. This is standard practice in comet science, and it usually works. Observations and models generally agree within reasonable margins. For 3i Atlas, they don't agree. When astronomers analysed the brightness and extent of the coma and tails, they calculated the mass of material being expelled. The amount of gas and dust needed to create the observed features is substantial. This mass loss requires a corresponding amount of energy to sublimate the ice and accelerate the gas. And here's where the problem emerges. The amount of energy required exceeds what you'd expect from solar heating of the object's apparent surface area. Let me break that down. Imagine the nucleus of 3i Atlas as a rough sphere. It's probably not perfectly spherical, but for estimation purposes, a sphere works. The surface area exposed to sunlight is roughly half the total surface area, since one side faces the sun and the other side is in shadow. Solar radiation hits that sun-facing hemisphere, and some fraction of that energy is absorbed. Not all of it, some reflects back into space, but let's say a reasonable percentage is absorbed. That absorbed energy heats the surface. When the surface temperature reaches the sublimation point for the ice is present, sublimation begins. The energy required to sublimate ice to break the molecular bonds, holding the solid structure together and allow molecules to escape, is called the latent heat of sublimation. For water ice, this is a known quantity. For carbon dioxide ice, it's different, but also known. You can calculate the maximum sublimation rate by dividing the incoming solar energy by the latent heat. This gives you a theoretical upper limit on how much ice can sublimate per unit time from the sun-facing surface. Multiply by the exposed surface area, and you get the total possible mass loss rate. In practice, the actual rate is lower because not all the surface is active, maybe only part of the surface has exposed ice, while the rest is covered by a thick dust layer that insulates the ice underneath. But even being generous and assuming high efficiency, the calculated mass loss rate for a typical comet nucleus of 3i Atlas's estimated size doesn't match the observed activity level. The jets are too bright. The coma is too extensive. The amount of dust and gas being expelled is more than you'd expect from the available surface area absorbing available sunlight. It's as if the object is somehow more efficient at converting solar energy into sublimation, or as if there's additional energy coming from somewhere else. Internal heat is an obvious candidate. Maybe the object has radioactive materials in its interior that provide heat, or maybe frictional heating from tidal stresses. But 3I Atlas isn't passing close enough to a massive body to experience significant tidal stress, and natural radioactive heating in comet-sized bodies is generally negligible compared to solar heating. Another possibility is that the object is smaller than estimated, meaning its surface arita-volume ratio is higher, which could allow more efficient heating. But estimates of its size come from observations of reflected light and thermal emission, and they're reasonably constrained. There's some uncertainty, but not enough to bridge the gap between expected and observed activity. Alternatively, maybe the object has a larger surface area than a simple sphere would suggest. Maybe it's highly irregular, with lots of nooks and crannies, or maybe it's porous, with internal voids that increase the effective surface area exposed to sunlight filtering through cracks. Porosity is a real factor in comets. Many comets are thought to be loosely bound aggregates of smaller chunks, sometimes called rubble piles, with lots of empty space inside. But even accounting for porosity, there are limits. Too much porosity, and the object becomes structurally weak, unable to hold itself together under its own gravity, let alone under the stresses of outgassing. And if the object is porous enough to explain the high activity level, you'd expect to see other signatures of that structure, perhaps rapid fragmentation or disintegration as weak points fail, or unusual rotational behavior due to uneven mass distribution. While 3I Atlas has shown some unusual behavior, it hasn't fragmented despite months of observation. It appears to be maintaining structural integrity, which suggests it's not on the verge of falling apart. This is what I call the surface area impossibility. The paradox that the observed activity requires more surface area or more energy than the object appears to have. It's not an absolute impossibility in the sense of violating physical laws. There are conceivable explanations, but it's an inconsistency that challenges our assumptions. And it gets worse when you combine this with the mass loss calculations. Sublimating ice and expelling dust doesn't just require energy, it also requires mass. Every kilogram of gas and dust blown off the nucleus is a kilogram the nucleus no longer has. Over time, as a comet makes repeated passes near the Sun, it loses mass, shrinks, and eventually either disintegrates or becomes a dormant, inert body once all the near-surface ice is gone. Astronomers can estimate total mass loss by integrating the observed outgassing rate over time. For 3I Atlas, given the activity level observed over the months it's been tracked, the total mass loss should be significant enough that the object should be noticeably changing. But initial observations suggest 3I Atlas hasn't fragmented or dramatically changed shape. It's possible that subtle changes are occurring that aren't obvious in the images. Maybe the nucleus is shrinking slightly, or maybe layers of surface material are being stripped away. But the kind of dramatic mass loss you'd expect from the observed activity should be producing visible changes, increased fragmentation, brightness variations, or changes in the jet structures as the surface evolves. The fact that the object appears relatively stable despite intense activity is another piece of the puzzle that doesn't fit neatly. Now, let's consider an even stranger possibility. What if the outgassing isn't primarily driven by solar heating? What if there's an internal energy source that's independent of the Sun? This is speculative, but it's not completely outside the realm of physics. Some comets show activity even when they're far from the Sun, in regions where solar heating should be minimal. This can happen if they contain super-volatile ices, materials like carbon monoxide or methane that sublimate at very low temperatures, or if there's some chemical energy source, like exothermic reactions between compounds in the nucleus. But for 3I Atlas, which is currently relatively close to the Sun inside Earth's orbit, at perihelion, solar heating should dominate any other energy source. An internal heat source powerful enough to produce the observed activity would need to be substantial, and sustaining that heat over time requires fuel, either radioactive decay, which is negligible in comets, or chemical reactions, which would deplete reactants over time. There's no evidence of unusual chemical composition that would support ongoing exothermic reactions on the scale needed. There's also the question of how energy is distributed within the nucleus. If there's an internal heat source, heat would need to conduct through the nucleus material to reach the surface where ice can sublimate. Comets are generally poor conductors of heat because they're porous and made of ice and dust, both of which are insulating. Effective heat conduction would require a different internal structure, maybe dense solid material with better thermal conductivity. But if 3I Atlas were made of dense rock or metal, it wouldn't sublimate and produce jets at all. All of these considerations bring us back to the central tension. The observations show activity levels inconsistent with what we'd expect from a typical comet nucleus heated by the sun. We're forced to either accept that 3I Atlas has extremely unusual properties, composition, structure, porosity, reflectivity that allow it to behave in ways no other observed comet does, or we consider that it might not be a comet in the conventional sense. It might be something else, a different class of object, perhaps something that's never been seen before, or perhaps something that formed through processes different from the accretion of ice and dust in a protoplanetary disk. And this brings us to a critical point in scientific reasoning. When do unusual observations justify reconsidering fundamental assumptions? There's a principle in science often summarized as Occam's razor. When faced with multiple explanations, prefer the simplest one. In this case, the simplest explanation is that 3I Atlas is an unusual comet with properties that stretch but don't break the boundaries of comet physics. Maybe it's unusually porous. Maybe it's unusually rich in volatile ices. Maybe its surface is unusually active. All of those are natural explanations requiring only that we extend our understanding of comets to include a wider range of possibilities. But there's another principle at play, the principle of consilience, which says that evidence from multiple independent sources should converge on the same conclusion. If we're seeing surface area problems, jet direction problems, collimation problems, and as we'll discuss next, problems with mass loss and acceleration, then at some point the simplest explanation becomes inadequate. The accumulation of anomalies suggests we might be dealing with something fundamentally different, and that's when science requires us to expand our hypothesis space, to consider possibilities that might have seemed unlikely, or even impossible under normal circumstances. 3I Atlas is pushing us toward that threshold, and the New Mexico images are one more piece of evidence that we're not dealing with a textbook comet. There's another layer to this mystery, and it has to do with how 3I Atlas is moving through space. When astronomers track objects in the solar system, they measure positions over time and calculate orbits. For most objects, gravitational forces dominate the motion. The sun's gravity pulls them, and if they pass near planets, those planets' gravity perturbs the orbit slightly. With enough observations, you can calculate a precise trajectory that predicts where the object will be at any future time. This works beautifully for asteroids and planets. For comets, though, there's a complication. Outgassing creates thrust. Think about it. When a comet vents gas, that gas carries momentum. Newton's third law applies for every action. There's an equal and opposite reaction. The gas shoots off in one direction, and the comet nucleus is pushed slightly in the opposite direction. This is the rocket effect I mentioned earlier. It's a real, measurable phenomenon. Astronomers account for it by including non-gravitational acceleration terms in their orbital calculations. These terms represent the additional forces acting on the comet beyond pure gravity. For most comets, the non-gravitational acceleration is small, a tiny nudge that slightly alters the orbit over time. It's detectable in precise measurements, but it doesn't dramatically change the comet's path. The size of the acceleration depends on the mass of the comet and the intensity of the outgassing. More outgassing means more thrust. Less mass means the same thrust produces a larger acceleration. It's basic physics. Force equals mass times acceleration. For 3I Atlas, the measured non-gravitational acceleration is significant. The object is not moving purely under the influence of gravity. It's accelerating in ways that require active outgassing to explain. This by itself isn't shocking comets do this. What's shocking is the magnitude. When scientists run the numbers estimating the thrust required to produce the observed acceleration and comparing that to the mass and size of the object, they find that the amount of material being expelled would need to be enormous. Calculations suggest the object would have had to lose a substantial fraction of its total mass estimates, suggest that the comet is losing an unusually large fraction of its mass, possibly around 10% or more just from the observed non-gravitational acceleration during the time it's been tracked. Now, losing 10 or 15% of your total mass is a dramatic change. For context, imagine if you suddenly lost 10% of your body weight in a matter of weeks. You'd notice. Your clothes wouldn't fit. Your face would look different. For a comet nucleus, losing that much mass means shrinking noticeably. the surface area changes. The shape might change, especially if outgassing is uneven, and if the object started out relatively small, losing that percentage leaves you with an even smaller object that's structurally weaker and more prone to fragmentation. Yet, as I mentioned earlier, observations of 3I Atlas don't show dramatic fragmentation or disintegration. The object appears to be holding together. It's still producing jets, still active, still moving along its trajectory without breaking apart. This creates a paradox. The motion says the object should have lost a huge amount of mass, but the appearance says it hasn't undergone the kind of structural changes you'd expect from that level of mass loss. There are a few ways to resolve this paradox, and none of them are entirely satisfying. One possibility is that the object's mass is larger than estimated, meaning the fractional mass loss is actually smaller. If 3I Atlas is denser or larger than the initial observations suggest, then losing a given amount of material represents a smaller percentage of its total mass, and the structural integrity concern diminishes. But refining mass estimates requires good data on the object's size and reflectivity, and those measurements come with uncertainties. While it's possible the mass is underestimated, it's unlikely to be off by enough to completely resolve the paradox. Another possibility is that the object has an unusual internal structure that allows it to lose mass without fragmenting. Imagine a hollow or partially hollow interior, a shell of material surrounding empty space. If outgassing occurs primarily from the outer shell, the object could lose significant shell mass while maintaining overall structural integrity, because the remaining shell is still thick enough to hold together. A hollow structure would also reduce the object's total mass, which would make the same outgassing thrust produce a larger acceleration, potentially explaining the observed non-gravitational acceleration with less actual mass loss. Hollow structures in natural objects are uncommon, but not impossible. Some asteroids are thought to be rubble piles with significant void space. Some comets may have internal cavities where subsurface sublimation has occurred, creating voids that later collapse or vent to the surface. But a sustained, large-scale, hollow structure is more unusual. It would require formation conditions or evolutionary processes that aren't typical for comets. And if 3I Atlas is hollow, that raises additional questions. How did it form that way? Did it form naturally through collisions or partial disruption of a larger body, or is there another explanation? This is where the conversation starts to veer into uncomfortable territory for mainstream science. A hollow or partially hollow structure maintained against collapse suggests some degree of structural engineering, whether natural or artificial. In nature, hollow structures arise from specific processes, lava tubes in volcanic rock, erosion cavities in sedimentary formations. But those processes are planetary, scale phenomena, not typical of small, cold bodies like comets. For a small object to have significant internal voids without collapsing under its own gravity, or breaking apart from rotational stress, it would need to have some structural support, either material strength exceeding typical comet compositions, or an architecture that distributes stress effectively. And that's a word you don't often hear in discussions of natural celestial bodies: architecture. Architecture implies design, intentionality, engineering. In the natural world, structure arises from physics and chemistry. Crystals form lattices, planets differentiate into layers, galaxies spiral due to rotation and gravity. But architecture deliberate arrangement of materials to serve a function that's the domain of biology and technology. When scientists start talking about potential internal architecture in a comet, even hypothetically, it's a sign that conventional explanations are being stretched to their limits. Let me be clear, I'm not saying 3I Atlas is artificial. I'm saying that the combination of observed non-gravitational acceleration, apparent structural integrity, and high activity levels creates a tension that's difficult to resolve with standard comet models. Natural explanations exist unusual composition, unusual structure, unusual formation history, but each requires invoking properties that are at the edge of or beyond what we've observed in comets so far. And when you have to keep invoking unusual properties to explain an object, at some point you have to ask whether the object itself is unusual in a more fundamental way. There's also a historical context here. When Comet Halley was studied in detail during its 1986 apparition, spacecraft observed jets venting from discrete locations on the nucleus. These jets produced measurable thrust, and astronomers calculated the expected impact on the orbit. The calculations matched observations well, confirming the rocket effect. but Halley is a well-studied, relatively large, active comet with a known history of repeated solar passages. 3I Atlas is different. It's an interstellar visitor, meaning it spent most of its existence in the cold of interstellar space, not regularly heated by a nearby star. Its composition and structure could be very different from solar system comets. Interstellar space is cold just a few degrees above absolute zero. Objects there would be frozen solid, with any volatile ices deeply buried under insulating layers of dust and refractory material. When such an object enters a solar system and begins to heat up for the first time, it might behave differently than a comet that's been through many heating cycles. Fresh ice might sublimate more vigorously. Stored volatiles might suddenly vent. The object might outgas more intensely than expected for its size. This first heating scenario could potentially explain some of the unusual activity, but it still doesn't fully account for the sunward jets, the collimation, or the combination of high activity with apparent structural stability. What we're left with is a picture of an object that's behaving in ways that challenge multiple aspects of comet physics simultaneously. The non-gravitational acceleration is just one piece of that picture, but it's an important piece because it's measurable and quantifiable. We're not relying on subjective interpretation of images, we have precise positional measurements showing that the object's motion doesn't match purely gravitational predictions. That's hard data, and it demands an explanation. And the explanations we have: unusual composition, unusual structure, first-time heating, they're plausible, but they're also somewhat unsatisfying because they require multiple coinciding unusual factors. The more unusual factors you need to invoke, the less likely it becomes that you're dealing with a typical example of a natural category, and the more you have to consider whether you're dealing with something that doesn't fit existing categories at all. Let me lay out the full picture, because what we've discussed so far, the jets, the surface area problem, the non-gravitational acceleration, those are just part of a larger set of anomalies that astronomers have documented. When you look at 3I Atlas as a whole, there are at least 12 distinct features or behaviours that are unusual, unexpected, or difficult to explain with conventional comet models. Individually, each might be dismissed or explained with special circumstances, but collectively, they form a pattern that's statistically improbable if this is just a normal interstellar comet. First, there's the trajectory itself. 3I Atlas is on a retrograde orbit, meaning it's moving through the solar system in the opposite direction to the planet's orbits. Retrograde orbits aren't impossible. Long-period comets from the Oort cloud often have them, but for an interstellar object, the retrograde alignment is notable. It means 3I Atlas approached the solar system from a specific direction in the galaxy, moving counter to the general flow of stellar motion in our local neighbourhood. That's not a violation of physics, but it's less common than prograde motion, and it adds to the object's distinctiveness. Second, the sunward jets. We've covered this extensively, but it bears repeating. Sustained jets pointing toward the sun are not explained by standard comet physics. Optical illusions can mimic sunward tails under specific geometric conditions, but the persistence of the antitail across multiple observation periods and changing viewing angles strongly suggests it's a real, physical feature. Third, the multidirectional jet structure. Normal comets show comas and tails that reflect averaged outgassing over rotation periods. Discrete jets are common, but multiple jets radiating in dramatically different directions simultaneously, maintained across long observation periods, suggest either very complex surface activity or internal structure that channels outgassing in specific ways. Fourth, the object's mass and velocity relative to other interstellar visitors. We've only confirmed 3 interstellar objects: Oumuamua, Borisov, and now 3I Atlas. Oumuamua was small, elongated, and showed non-gravitational acceleration despite no visible outgassing, a mystery in itself. Borisov was more comet-like, with visible coma and tail, but otherwise unremarkable. 3I Atlas falls between these extremes but leans toward the unusual end. Its velocity relative to the Sun and its trajectory suggest it wasn't gravitationally perturbed much by previous stellar encounters, meaning it's been travelling through interstellar space for a very long time, possibly since the early galaxy. Fifth, the timing and trajectory alignment. This is where things start to get eerie. Astronomers calculated the trajectory of 3I Atlas backward in time, tracing where it came from. The direction of origin points to a region of sky within a few degrees of the location from which the famous WOW signal was detected in 1977. The WOW signal was a powerful narrowband radio signal detected by the Big Ear telescope at Ohio State University. It lasted for the full duration of the observation window about a minute and has never been detected again despite repeated searches. Its origin remains unexplained. The fact that 3i Atlas's trajectory traces back to a similar region of sky is almost certainly a coincidence. Space is vast, and a few degrees is a large angular area, but it's the kind of coincidence that captures the imagination and adds narrative weight to the mystery. Sixth, the object's chemical composition. Spectroscopic analysis of the gas emitted from 3i Atlas shows unusual ratios of elements. Specifically, the nickel-toyon ratio in the gas is much higher than what's typical for solar system comets. Most comets have low metal content. They're mostly ice, dust, and organic compounds, with trace metals. The high nickel-ion ratio in 3i Atlas's emissions is reminiscent of certain types of metallic alloys, industrial alloys even. Now, before jumping to conclusions, it's important to note that measuring elemental abundances from spectroscopy is complex and subject to uncertainties. Different ionization states, temperatures, and densities in the coma can affect the observed spectrum. But even accounting for these factors, the nickel-ion ratio seems anomalously high. If this measurement is accurate, it suggests the object either formed in an environment very different from our solar system's protoplanetary disk, or it has a composition that's not typical of comets. Seventh, the water content, or rather, the lack of it. Comets are often called dirty snowballs because they're thought to be mostly water ice with dust and other materials mixed in. Spectroscopic observations of 3i Atlas suggest the water content appears to be significantly lower than typical solar system comets, with a higher proportion of carbon dioxide detected, according to some estimates. That's dramatically lower than typical comets, which can be up to 50% water ice by composition. Low water content doesn't mean the object isn't a comet, but it does mean it's an unusual one. Perhaps it formed in a region of its origin stellar system, where water was less abundant, or perhaps it lost water over billions of years in interstellar space through slow sublimation or radiation processing. Either way, it's another anomaly to add to the list. Eighth, the polarization of reflected light. When sunlight reflects off a comet's dust grains, the reflected light becomes partially polarized. The degree of polarization depends on the size, shape, and composition of the dust particles. Astronomers can measure this polarization to learn about the dust properties. For 3i Atlas, the polarization measurements showed something unusual: negative polarization at certain angles. Negative polarization is rare and typically indicates either very small particles or unusual particle shapes and compositions. This adds to the picture of an object with properties that don't match the standard comet template. Ninth, the object's brightness variations and color as it approached perihelion. As comets approach the sun and heat up, they typically brighten due to increased outgassing and dust production. 3i Atlas did brighten, but the rate and pattern of brightening were unusual. The color of the reflected light also changed in ways that suggest changes in the dust-Togas ratio or in the types of materials being sublimated. These variations could indicate layers of different composition being exposed as the surface erodes, or they could indicate internal structure affecting how heat propagates through the nucleus. 10th, the surface area problem. We've discussed this in detail. The observed activity level requires more energy or more active surface area than a simple spherical nucleus of the estimated size should provide. 11th, the non-gravitational acceleration and implied mass loss. Also discussed in detail. The object's trajectory shows acceleration consistent with rocket effect thrust from outgassing, but the amount of mass loss implied by that thrust level is difficult to reconcile with the object's apparent structural integrity. And 12th, the collimated jet maintenance across distance and time. The jets, particularly the main tail and the antitail, show a degree of collimation and persistence that's at the high end of what's observed in comets, suggesting either unusually well-organized outgassing or internal channeling of gas flow. 12 anomalies, 12 features that individually might be explained but collectively paint a picture of an object that's unlike any comet we've thoroughly studied. Now, let's think about probability. If each anomaly has, say, a 10% chance of occurring in a typical comet, which is generous, some of these features are rarer than that the probability of all 12 occurring together in one object is vanishingly small. Of course, these anomalies aren't entirely independent. Some might be related or caused by common underlying factors. But even accounting for correlations, the cumulative improbability is striking. This is what scientists call a high-dimensional outlier. In any population, there are outliers, individuals, or examples that fall outside the normal range in one or two characteristics. But an outlier across many independent characteristics simultaneously is extremely rare. And when you encounter such an outlier, it often means you're either seeing the extreme tail of natural variation, or you're looking at something that doesn't actually belong to the population you're studying. In the context of 3i Atlas, the question becomes, is this an extreme example of a natural interstellar comet so unusual that it redefines the boundaries of what we consider possible for comets? Or is it something else entirely that superficially resembles a comet, but has a different origin? That's the question dividing the scientific community right now, and it's not a question with an easy answer, because we don't have enough data yet. We've only observed 3 interstellar objects. That's not nearly enough to establish what's normal and what's not, for objects originating outside our solar system. Every stellar system is different. Planetary formation processes vary. The interstellar environment varies. It's entirely plausible that interstellar comets are more diverse than solar system comets simply because they come from a wider variety of formation environments. But there's a flip side to that argument. If interstellar comets are highly diverse and we're only now beginning to observe them, then we should see a wide range of properties as we detect more of them. We should see some that look like solar system comets, some that are very different, and everything in between. What we've seen so far is Oumuamua, which was so unusual it sparked debates about whether it could be artificial. Borisov, which was relatively normal, and now 3i Atlas, which leans heavily toward the unusual end. Small sample size, yes, but the trend suggests that interstellar visitors may indeed have a higher incidence of anomalous properties than we expected. And here's where the discussion becomes philosophical as much as scientific. How do you investigate something that doesn't fit your models? Do you stretch your models, add new parameters, incorporate new physics, expand the range of what you consider possible until the observations fit? Or do you consider alternative hypotheses that might not fit within traditional frameworks? Both approaches are valid in science, but they lead to different types of investigations and different types of conclusions. Stretching models is conservative. It respects the accumulated knowledge and assumes that nature operates within known bounds, just with more variety than we initially thought. Considering alternative hypotheses as exploratory, it opens the door to genuinely new phenomena, but also increases the risk of chasing explanations that turn out to be wrong or unnecessary. Right now, with 3i Atlas, both approaches are being pursued. Some scientists are working to refine comet models, incorporating the possibility of unusual compositions, structures, and formation histories that could explain the observations naturally. Others are asking whether we should at least investigate the possibility that some interstellar objects might not be natural at all, that in a galaxy billions of years old with potentially millions of technological civilizations past and present, we might occasionally encounter artifacts, remnants, probes, or derelict spacecraft drifting through the void. That second approach is controversial, not because it's inherently unscientific, but because it invokes hypotheses that are difficult to test, and that carry significant implications if they turn out to be correct. The scientific community's response to 3i Atlas has been, to put it mildly, divided. Not in a hostile or acrimonious way, scientists are trained to disagree productively, but divided in terms of how seriously to take the possibility that this object might be something other than a natural comet. And that division reveals something important about how science approaches the unknown, especially when the unknown touches on questions that have cultural and philosophical weight beyond pure physics. On one side, you have the majority view, which is conservative and rooted in the principle that extraordinary claims require extraordinary evidence. This perspective holds that 3i Atlas, despite its unusual features, is most likely a natural object, a comet or comet-like body that formed in another stellar system, under conditions different from those in our solar system. The anomalies we're seeing reflect our limited understanding of interstellar object diversity, not evidence of anything artificial or engineered. Proponents of this view point out that we've only observed a handful of interstellar visitors, far too few to establish what's typical. Every new observation expands our understanding of what natural objects can do. Oumuamua surprised us with its elongated shape and non-gravitational acceleration, without visible outgassing. Borisov looked more like a typical comet but still had its quirks. Now 3i Atlas is teaching us that interstellar comets can have unusual compositions, unusual activity patterns and unusual trajectories. That's science working as it should, observations challenging models being updated to accommodate new data. This view is not dismissive, it's methodologically careful. Scientists holding this position acknowledge the anomalies. They're publishing papers analysing the data, running simulations, proposing mechanisms that might explain what we're seeing. The high nickel-iron ratio. Maybe 3i Atlas formed in a stellar system with a different metallicity than ours, where heavy elements were more abundant in the protoplanetary disk. The low water content? Maybe it formed in the outer regions of its system where water ice was less available, or maybe it's been processed by cosmic rays and radiation during its interstellar journey, selectively depleting volatiles. The sunward jets? Maybe there's a mechanism we haven't fully appreciated, perhaps internal heat, from radioactive decay or exothermic chemical reactions driving sublimation independent of solar heating, creating jets that aren't aligned with the sun's direction. None of these explanations are fully satisfying on their own, but together they sketch a picture of an exotic but natural object. And the conservative view argues that this picture is preferable to invoking more speculative hypotheses until we've exhausted natural explanations. This is a reasonable and scientifically sound approach. It respects the history of astronomy, which is full of instances where seemingly mysterious phenomena turned out to have natural explanations once better data or better theories became available. Pulsars were once jokingly called LGMs, little green men, because their regular radio pulses seemed too precise to be natural. They turned out to be rapidly rotating neutron stars. Quasars were mysterious ultra-bright objects that defied explanation until we understood they were supermassive black holes accreting matter in distant galaxies. So the conservative view on 3i Atlas is, let's gather more data, refine our models, and assume it's natural unless proven otherwise. And to be clear, this is the dominant view in the astronomical community. Most professional astronomers working on 3i Atlas are pursuing this line of investigation. But there's another perspective, a minority view but one articulated by credible scientists with solid reputations. This view, most prominently associated with Harvard astronomer Avi Loeb, argues that we should seriously investigate the possibility that some interstellar objects might be artificial technological artifacts from other civilizations. Not because there's definitive proof that 3i Atlas is artificial, but because the hypothesis is scientifically plausible and the potential implications are profound enough to warrant investigation. Here's the reasoning. Humanity has been launching objects into space for decades. Some of those objects, like the Voyager probes, like the New Horizons spacecraft that flew by Pluto, are on trajectories that will eventually take them out of the solar system. In millions or billions of years, there'll be interstellar objects drifting through the galaxy. If they happen to pass through another star system, they'll be detected as interstellar visitors by any civilization capable of observing them. They'll show unusual properties, non-gravitational acceleration from any remaining maneuvering fuel or from the solar wind acting on their large antennae, unusual reflectivity from metal and plastic surfaces, unusual trajectories that don't match natural orbits. To observers in that distant star system, Voyager or New Horizons might look like anomalous objects that don't fit comet or asteroid models. Now, humanity is young, we've been technological for only a tiny fraction of cosmic time, but the galaxy is old, over 13 billion years. Stars and planets have been forming for most of that time. If even a small fraction of stellar systems develop life, and a small fraction of those develop technological civilizations, and those civilizations last for any significant length of time and engage in space exploration, then the galaxy should contain a large number of technological artifacts. Most would be ancient, long since defunct, drifting through interstellar space as debris from civilizations that rose and fell billions of years ago. Occasionally one of those artifacts might pass through our solar system, and if it does, we should be able to detect it, especially if it's reflecting sunlight or outgassing materials. This hypothesis doesn't require invoking active alien spacecraft visiting us intentionally. It simply requires that technological civilizations exist elsewhere in the galaxy and that they produce artifacts that eventually become interstellar travelers. Given the size and age of the galaxy, that's a reasonable assumption, and if it's reasonable to assume such artifacts exist, then it's reasonable to consider that some of the anomalous, Interstellar objects we detect might be examples of such artifacts. Loeb has been vocal about applying this reasoning to Oumuamua and now to 3i Atlas. He's not claiming definitive proof, he's arguing for open-minded investigation. His position is that when we encounter an object with multiple anomalies that are difficult to explain with natural models, we should investigate both natural and artificial hypotheses in parallel, using the same rigorous scientific methods for both. Design follow-up observations that could distinguish between the two. Look for signatures that would be expected in artificial objects but not in natural ones, radio emissions, infrared signatures consistent with waste heat from power sources, organize structures visible in high-resolution images, trajectory changes that suggest propulsion or navigation. This approach is controversial, not because it's unscientific, but because it challenges certain assumptions about how science should prioritize hypotheses. The traditional approach is to exhaust natural explanations before considering extraordinary ones. Loeb's approach is to investigate natural and extraordinary explanations simultaneously when the data justifies it. Both are valid scientifically, but they reflect different philosophies about how to allocate limited resources, telescope time, funding, researcher attention. Critics of Loeb's approach worry that taking the artificial hypothesis seriously gives it unwarranted credibility and might mislead the public into thinking there's stronger evidence for alien artifacts than actually exists. They also worry that it distracts from the real scientific work of understanding natural phenomena. If every unusual observation triggers speculation about aliens, we'll waste time chasing signals that turn out to be natural, and will undermine public trust in science by appearing to endorse sensational interpretations prematurely. Defenders of Loeb's approach argue that science shouldn't be afraid to investigate uncomfortable hypotheses, and that the potential payoff discovering evidence of extraterrestrial technology is so significant that even a small probability justifies serious investigation. They also argue that investigating the artificial hypothesis doesn't mean abandoning the natural one. Both can be pursued in parallel, and the investigation itself will generate valuable data regardless of the outcome. Where does the truth lie? Honestly, both sides have merit. The conservative approach has the weight of scientific tradition, and a strong track record. Most mysteries do turn out to have natural explanations. But the exploratory approach acknowledges that we live in a universe where technological civilizations are possible, and that occasionally we might encounter their artifacts. The key is to remain rigorous, to base conclusions on evidence rather than speculation, and to communicate clearly about what we know and what we don't. What's frustrating for those of us watching this unfold is the lack of definitive data. What we need are close-up observations, high-resolution images, spectroscopic data across multiple wavelengths, and ideally, a mission to intercept and study the object directly. Unfortunately, 3i Atlas is moving fast. It's on a hyperbolic trajectory that will take it out of the solar system and back into interstellar space. By the time a mission could be planned, funded, and launched, the object will be long gone. We're limited to telescopic observations, and while those provide valuable data, they have inherent limitations in resolution and detail. So the debate continues. Papers are being published, data is being analysed, and scientists on both sides are making their cases. And meanwhile, 3i Atlas continues its journey, indifferent to our debates, carrying its secrets with it. Whether it's an exotic comet or something more, it's forced us to confront the limits of our knowledge and the assumptions we make about the universe. And that, in itself, is valuable. Science thrives on questions, on mysteries that don't have easy answers. 3i Atlas is giving us exactly that. So where do we go from here? That's the question on everyone's mind, and the answer is both exciting and frustrating. Exciting because we're actively observing something unprecedented, gathering data in real time, watching the story unfold. Frustrating because 3i Atlas won't stay in our neighbourhood forever. Interstellar objects pass through the inner solar system briefly, a matter of months, or at most a year or two, and then they're gone, receding into the darkness, becoming too faint to observe with current telescopes. Every observation window is precious. Every night of clear skies, every telescope pointed at this object, every spectrum captured adds to our understanding. But there's a ticking clock. Soon, 3i Atlas will be too far away and too dim to study in detail, and we'll be left with whatever data we manage to collect during this narrow window. Astronomers around the world are prioritizing observations. Telescopes in both hemispheres, professional and amateur, are tracking the object's position, capturing images and recording spectra. Every piece of data goes into a growing archive that scientists will analyze for years to come. We're looking for changes, variations in brightness, shifts in the jet structures, signs of fragmentation or disintegration, spectral lines that indicate new materials being exposed or old materials depleting. These changes tell us about the object's composition, structure, and internal processes. There's also the possibility of detecting radio or infrared emissions if the object has any kind of internal heat source, or if there are mechanisms generating electromagnetic radiation. Radio telescopes have been used to search for signals from Oumuamua, and similar searches are being conducted for 3i Atlas. So far, nothing has been detected, but absence of evidence isn't evidence of absence, especially when the sensitivity and coverage of searches are limited. A faint signal, a brief emission, a narrow band transmission, any of these could easily be missed if the telescope isn't pointed in the right direction at the right time and tuned to the right frequency. Infrared observations are particularly valuable because they reveal thermal emission heat radiated by the object itself, rather than reflected sunlight. If there's an internal heat source, infrared would detect it. If there are temperature variations across the surface, infrared would map them. These observations can constrain models of the object's internal structure and composition. Some of the most detailed studies of comets in recent years have come from infrared space telescopes like Spitzer and the James Webb Space Telescope. JWST in particular has the sensitivity and resolution to potentially reveal fine details in 3i Atlas's Comet and jets if observing time can be allocated before the object becomes too faint. Then there's the question of future interstellar visitors. 3i Atlas is the third confirmed interstellar object, but it won't be the last. Current estimates, based on the detection rates of Oumuamua, Borisov and 3i Atlas, suggest that interstellar objects pass through the inner solar system fairly regularly, perhaps one or more per year. Most go undetected because they're small, faint, or pass through when telescopes aren't looking in the right direction. But as survey telescopes improve instruments like the Vera Rubin Observatory, which will begin operation soon, and the proposed Large Synoptic Survey Telescope Network detection rates will increase, we'll find more interstellar visitors, and each one will add to our understanding of what's out there. We'll start to build a statistical picture of interstellar object properties, which will help us determine whether 3i Atlas is truly unusual or just one example of a diverse population. And here's where things get really interesting. If we detect interstellar objects early enough in their approach to the Sun, we could potentially launch missions to intercept them. This sounds like science fiction, but it's being seriously considered. Fast flyby missions using gravity assists from planets to gain speed could reach an interstellar object within a few years if launched promptly. A spacecraft passing close to the object could capture high-resolution images, measure its mass and density using gravitational deflection, analyze its composition with onboard instruments, and even deploy small probes or impactors to study its interior. There are challenges, of course. Interstellar objects move fast, much faster than typical comets or asteroids, so any intercept mission would be a high-speed flyby, not a leisurely rendezvous. The spacecraft would have only a brief window to collect data as it whips past the object, but even a brief encounter would provide orders of magnitude more information than telescopic observations. We'd see the surface up close, resolve features smaller than a meter, measure properties that are impossible to determine from afar. A mission like this could definitively answer whether an object like 3i Atlas is an exotic comet or something else entirely. Proposals for such missions have been discussed in space agencies. The European Space Agency considered a mission to intercept Oumuamua, but concluded it would require too much change in velocity to catch the object before it left the solar system. More realistic might be a standby mission concept, a spacecraft kept ready to launch on short notice when a new interstellar object is detected. This would be expensive and logistically challenging, but the scientific payoff could be enormous. If the goal is to determine whether any interstellar objects are artificial, a close-up mission is the most direct way to answer the question. In the meantime, we have the data we're collecting now, and it's not trivial. Scientists will spend years analysing the observations of 3i Atlas, extracting every bit of information from the images, spectra, and positional measurements. There will be papers published, models refined, debates in conferences and journals. The object will become a case study in interstellar visitor science, referenced and reanalyzed as our understanding evolves. And regardless of whether 3I Atlas turns out to be an exotic comet or something more, it's already taught us valuable lessons. One lesson is humility. We thought we understood comets well. We've studied them for centuries, sent spacecraft to them, even landed on them. But an interstellar visitor comes through, and suddenly our models struggle to explain what we're seeing. That's a reminder that the universe is larger and more diverse than our local experience. Our solar system is just one example of planetary system formation and evolution. Other systems formed under different conditions, with different elemental abundances, different dynamical histories. Objects from those systems will behave differently, look different, challenge our assumptions. And that's okay. That's how science progresses. Another lesson is about the importance of being open to unlikely possibilities. The debate over whether to seriously investigate artificial origins for objects like 3I Atlas isn't just about this one object, it's about how science handles questions that sit at the boundary of the known and the speculative. We can't investigate every wild hypothesis, resources are limited, and most speculation turns out to be wrong. But we also can't dismiss hypotheses purely because they're uncomfortable, or because they challenge our sense of humanity's place in the universe. The question of whether we're alone, whether other technological civilizations exist, whether we might someday encounter their artifacts, that's one of the most profound questions we can ask. And if we're not willing to seriously investigate it when we have the opportunity, we might miss something extraordinary. And there's a third lesson, one that's perhaps more personal. We live in a time when the universe is revealing its mysteries to us at an unprecedented rate. Every week, it seems, there's a new discovery: exoplanets orbiting distant stars, gravitational waves from colliding black holes, images of galaxies from the early universe. We're witnessing the golden age of astronomy and astrophysics, and occasionally something comes along that's not just another data point in a well-understood category, but something genuinely puzzling, genuinely new. 3I Atlas is one of those things. Whether it's an exotic comet or something more, it's here, it's observable, and it's challenging us to think harder and look closer. You, watching this, are part of that story. You're not a passive consumer of science news, you're a witness to an active investigation. Right now, somewhere, a telescope is gathering photons that travelled across space, reflected off 3I Atlas, travelled millions more kilometres to Earth, and are being captured and recorded. Those photons carry information about composition, about motion, about structure. Scientists will decode that information, but it started with the object itself, an interstellar traveller that's been journeying through the galaxy for who knows how long, and that happened to pass through our solar system at a time when we have the technology to observe it. That's not just science, that's connection to something vastly larger than ourselves. And here's what I find most compelling. We don't know how this story ends. The New Mexico images are remarkable, but they're not conclusions, they're data points in an ongoing investigation. More observations will come, more analyses will be published. Maybe we'll find a natural explanation that accounts for all the anomalies, some combination of unusual composition and structure that makes 3I Atlas an outlier, but still a member of the natural comet family. Or maybe we'll find something that doesn't fit, something that forces us to expand our categories, to consider possibilities we've only speculated about until now. Either outcome is significant. Either outcome changes how we think about the universe and our place in it. So what happens next is this. We keep watching. We keep analysing. We keep asking questions. We stay curious, stay rigorous, and stay open to where the evidence leads. Because that's what science is, not a collection of answers, but a process of inquiry. And right now, 3I Atlas is inviting us to inquire, to wonder, to engage with the unknown. And that invitation, more than any single answer, is the heart of discovery, is what makes us human. This drive to understand, to explore, to look at something strange and ask, what is that? And whether 3I Atlas is a comet from another star or something we've never seen before, it's giving us the chance to ask that question and to pursue the answer with every tool we have, and that ultimately is what makes this moment so extraordinary.